I'll take the homeworks. Okay, so on a week ago, almost, a week ago Thursday, we introduced the idea of bipartite graphs. So a graph is bipartite if the vertices can be partitioned into two sets, let's say X and Y, and it's a partition, so no vertex is in more than one of these sets, and every vertex is in at least one. And the edges are a subset of X and X and Y and Y. So the pairs XY. And what we know is that in a bipartite graph, a graph is bipartite, then it contains no odd cycles. So I'll write it like that for a moment. Well, if it contains no odd cycles, then what are the only cycles that it contains? Even cycles. Okay? What if it contains no even cycles?
Then it contains no cycles.
Then it contains no cycles. Okay, so that's what's next. A tree. Let's actually. So he doesn't define this yet, but this is where we're aiming towards. Now let's define a tree. A tree is a connected graph with no cycles. What if I drop connected? What do you think it's called? So if we drop connected, then and I look at any one of the components being the connected components, then each component must be what? One more time. So we're going to define a graph that has no cycles. If we add, again, a connected graph that has no cycles is a tree. So if I drop connected, then what must this graph look like?
Multiple trees.
Philosophically.
More trees.
More trees. Okay, so I don't know how many there are. So it's a union of trees. And mathematicians sometimes have an odd sense of humor. So what do you think a union of trees would be called?
Forest.
Forest.
No way.
Yep. So, more general than a tree is a connected graph with no cycles. A forest is a union of trees. Forest is a union of trees. And of course, it also contains no cycles. Okay. So over the 5-day weekend, from last Thursday to today, what can you tell me about the number of, did I ask you to find the number of trees on, did I tell you to draw trees? Did I ask you to draw trees? I did. So how many trees did you draw? 6 trees. So that's 6 trees on 6 vertices. Is that what I asked you? I only see 6. Is 7? Okay. So how many trees? Different. And that becomes a problem. But how many different trees on 7 vertices are there? So who started out? How many different trees are there on, and remember, I'm only talking about trees at this point. How many different trees are there on one vertex? One. There it is.
It doesn't have to have it.
Doesn't have to have, so notice, then it doesn't, does this tree have any cycles? Is this tree connected? Okay, I mean, so there's this vacuous idea of connectivity, so it's connected because I can get from any one vertex to any other vertex. It's not very interesting, but I can get there. Okay, so it's connected, has no cycles. Okay, and what about 2? Okay, so if I have 2 vertices, I know it's got to be, it has to be a connected graph. So now the number of trees on 2 vertices, the number of different trees on 2 vertices is 1. 3 vertices? Nope, too many. Anybody find another tree on 3 vertices? At some point it's going to get interesting. Okay, so there's 1 vertex on 1 vertex, 1 tree on 1 vertex, 1 tree on 2 vertices, 1 tree on 3 vertices. 4 vertices? Well, I know when I get to 7, there's at least 6. What about 4 vertices? There are 2? Are you telling me or asking me? 2. Okay, what are they? No, now what's this called? A path. And what's this called? We gave this a name, didn't we?
A star.
It's star. Okay, so this is P4, and this is K13. So it looks like there aren't too many trees. Okay, just anybody look up how many trees there are on. Okay, so there's 2. How many trees on let's see, what am I up to? How many trees on 5 vertices? Let's actually draw those. How many trees on 5 vertices? There's 2 easy ones, right? There's P5, and there's the star. Are there any more?
you have a root. and
Okay,
then-
so I gotta,
And then 3. Yeah, and then I'll
like that?
go.
Are there any more? Okay, so here are the trees on 5 vertices. So it goes, let's see, we got 1, 1, 1, 2, 3. How many trees? So maybe it follows some pattern. Okay, I'm not gonna, you should draw, you should be practicing, you should not be practicing. Draw trees. It's good for you. Okay, so let's see, I'm up to, that's 3, up to, so how many vertices? That's 5 vertices, 6 vertices. Draw some trees on 6 vertices. And let me do the easy ones. The easy ones are P6. And the star. Notice this is P6, and this is K15.
Is it really only 3 on that one? Because the one with the triangle on the bottom, couldn't you just do 1 that goes this way and then have 3 tendrils, 3 parts of your star?
Wait a second. That?
Yeah.
Oh,
Oh, I get it, because they're all part of the same central one. Okay.
yeah, don't be fooled by the geometry. The geometry doesn't matter in this class. The only thing that matters is the edges. Notice one more time, this tree is this tree. Right? We have a central vertex, better known as the center of the star. This is K1, this is K, notice it's a complete bipartite graph. This is K14.
Can you call the one you drew to begin with a K14 also?
Sure, of course. You mean this one?
Yeah,
Yeah.
so it doesn't have to be shaped like it.
Doesn't have to be shaped. There's no, the artistry doesn't, let me just, even though this is called a path, right? This is P5. This is also a path.
Didn't have to be in a certain
Okay. So there's no, the way you draw these things doesn't matter.
All right, because it's introducing this thing. Okay, thank you.
I'm sure there are more than 2 trees of order 6. Anybody got another one?
Yeah. So we can have one vertex in the middle, and there's a two vertices pass near it. Yes.
Okay. Not all graphs have nice names. This doesn't have a, path, star, who knows? Okay. Any more?
Yeah. So we can have one vertex with three one vertex pass near it, and 2 vertices pass another path. So
I think you need one more straight down.
yeah. Yes.
Good, okay.
Oh, so the first one you drew is what you were trying to discuss.
Any more?
Yeah.
No one looked this up?
So
Google should be your friend.
so we can also have the one vertex in the middle and yes. Mhm.
1, 2, 3, 4, 5.
We can still have 6.
We have to have 6.
Yeah.
Why do we have to have 6?
Well, because we have. Oh, no. Oh, no.
The same
Oh, no,
as the
this
one back.
is that this?
It's the one right back.
Is that, oh, that's this.
Yeah.
Well, that's why I didn't see it. Okay, so I believe there's 6.
Yeah, so we can have
Do you have-
5 vertices plus this,
A path of 5,
yes,
and
yeah.
is that this?
So change the position of this small shift. Yes.
Yes.
Okay,
Now,
and okay, so this one looks different.
Yeah.
6. Okay, and there are 6. 6 trees of order 6, so there must be 7 trees of order 7? Just take a minute. I mean, there are 2 obvious ones, right? There's a star and there's a path. Anybody actually look for the number of trees of order 7? You draw 10? 10 trees of order 7? It's like an auction. Anybody got more than 10? And this is part of the problem, is how do you categorize these? I believe that there are 11 trees of order 7. 11 different trees of order 7. I believe that there are 23 different trees of order 8. I believe there are 47 different trees of order 9. Okay. I just wrote down for my own good. So, how many trees of order 20 do you think there are? How many different trees of order 20? Ballpark? A lot.
2 to the 20?
2. Oh, that's a real lot. Okay, there are 317,955. That's not 2 to the 20, but it's pretty big. 30. There's 469,566,585. Okay, and believe it or not, there are programs that can actually generate all the trees, all the different trees depends on how much time you have for any given number of vertices. So this idea of trees turns out to be pretty important. Okay, so let's talk about some properties of trees. So pick your favorite tree, pick your favorite tree. Let's see, of order 8. This is mine. Don't choose mine. Now, it's connected, so if I close my eyes and I pick 2 vertices, the graph is connected. What can you tell me about between those 2 vertices, x and y? There's they don't have to be an edge, right? Right, so if I'm going to close my eyes and pick 2 vertices, like this vertex and this vertex. There's a path. How many paths? Okay, so a graph G is a tree if and only if it is IFF. If and only if it is connected. Well, let's see. Connected contains is a tree of order n. Order means the number of vertices. A graph G is a tree of order n if and only if it is connected, contains n minus 1 edges. It's connected, and for all, is that okay for all? For all vertices, x and y, what can you tell me? It's connected, so what can you tell me, what about x and y? It's connected.
It's exactly one path.
Ah, how many?
One.
1. For all x and y in the vertex set, there exists exactly one xy path. Okay. That's what makes it a tree. That's what makes it interesting. So if between any two vertices in a tree, so imagine here's my tree, there's exactly one path between them. If there was a second path between these 2 points, if there was a second path, now let's see, it doesn't have to go out, it could go like this. If there was a second path, then what would necessarily result? What's this?
A cycle.
A cycle. Okay, and what do we say a tree was? There's no cycles. Okay, so we get, in any tree T, for all pairs of vertices, x and y in the vertex set, there's exactly one XY path. So all of these are equivalent definitions of trees. And as we're going to find out in the next several sections, it turns out that trees are pretty important in helping us determine a lot about the underlying graph. If I give you a graph, then you can look at that graph and try and find a tree, a spanning tree, a tree that contains all the vertices in G. So let G be a graph. If G contains a spanning tree, then G is connected. So this is one way for us to learn whether a graph is connected. Okay. Trees turn out to be pretty important. Trees, so we're not going to do much as far as applications go, but if you were to look at applications, trees being the skeletal form of a graph becomes an important concept when you look at actual applications. If you go further in graph theory, that's one of the things you want to look at is a little bit about the applications. Okay, so trees, I got a tree, it's a connected graph, contains no odd cycles, and do I know how many edges it has? So let's see, I know a tree, one tree of order n. There's n vertices. This is a tree of order n. This is better known as the path. How many edges does the path have? N minus 1. The other tree on n vertices that I know, right off the bat, is the star. It's got n vertices, so there's n minus 1 end vertices. Has n minus 1 edges. How many, sorry, n minus 1 edges? So the path has how many edges?
N minus 1,
N minus 1. The star has how many edges?
N minus 1.
And in fact, every tree of order n has n minus 1 edges. Every tree of order n has n minus 1 edges. Okay, and that's we can characterize trees because they're connected and they contain n minus, they're connected of order n. You have a connected graph of order n that has at least n minus 1 edges, and every tree that has n minus 1 edges every connected graph with n minus 1 edges is a tree. Okay, n being the number of vertices. Okay, questions about that? Again, for applications as we move on, we'll see more of these trees pop up as a way to get to the root of especially connected graphs. If you're trying to do something with a connected graph, we're going to want to look at an underlying spanning tree. Okay, so again, just if you take a connected graph, and it doesn't have to be, now it doesn't have to be a tree, a connected graph G, then we will look for a spanning tree. So we'll look for a tree that contains all the vertices spanning, contains all the vertices and some of the edges. Okay, so one thing we'll actually try and do, if I have a graph G, and I can find a graph G, and I can find a tree that contains all the vertices, then we know the graph is connected. So we'll use spanning trees to help us to actually prove that graphs are connected. Okay? Questions about that? Okay, I'm going to come back to trees in a moment, but I want to talk about one of the problems from the homework that I got several questions about. Has nothing to do with trees. But it is a fundamental concept. This leads to a fundamental concept in graph theory. So the problem that I want to look at is, I'll never find it. Let's see. I can tell you what the problem is. You tell me which one it is. So show that in every graph of order 5, either the graph contains a P3, okay, so let n be 5. Either G, so we have a graph of order 5, G contains a P3, or G complement contains a K3, a C3 which is a K3. Okay. Now this idea of looking at a graph and then its complement and comparing the two becomes really pretty important. So does anybody, which problem was this?
Page 93, number 20.
Page 93, number 3.
95.
95, number 3. Okay, so
Number 21.
number 12, of course, number 21. Was this the one that I gave you the wrong page for?
No.
Okay, one of them I gave you the wrong page. I just got very excited and put down the wrong page. So, who thinks they have a nice proof? G is 5. Either G contains a P3 or the complement contains a C3 or a K3. Anybody? Okay.
So if you take a graph of order 5,
Okay, so listen, here's my graph. Here are my 5 vertices.
and I actually think we can do this with 4, or maybe there was a mistake in my proof, but I might be jumping ahead.
Hold on.
Okay.
Okay, we're gonna come back to that.
Okay, so if you just take one of these vertices,
Okay,
and we call it A, I guess.
okay, A,
And then, so in either G or G complement,
Uh-huh.
A has a degree of at least 2.
okay. So in the whole graph, and the possibility for the degree of A is 4 in the whole graph. So in all the edges, either the edge is in G or it's in G complement. Okay,
So I'm not sure if we're in G or G complement, but we'll just say 2 of those other edges, we call them B and C, and say both of them are connected to A.
okay. So if A is adjacent to B and C,
And now I figure we have 2 cases. Either,
we need another case?
well, either B and C are connected or they're not connected.
Do we need another case? This is G, right? This is G.
Oh, it's either G or G complement.
Well, let's stick with, this is G. Suppose A is adjacent to 2 vertices in G.
Mhm.
Okay, this is G, and suppose A has degree 2.
Gotcha.
Then what is this?
Then this is G.
So either G contains a P3, up, so we're done. This is a
Oh,
P3.
okay. Oh. Oh, okay. I was thinking, for some reason, I was thinking a P3 would have 3 edges.
Yeah,
So
yeah.
I think I
so we're
did
gonna come
too hard
back
of a
to-
problem.
we're-
Okay.
That's not true. Okay, and we're gonna talk about that in a second.
Okay.
Okay, so P3, this is P3. Path on 3 vertices. Okay, so one more time. If A has degree 2 in G, then there's a P3. Okay, so the degree of A must be at most 1. Okay, so in the complement, I'm going to draw the complement edges in black. Is that okay? I'm going to draw the complement. So A has degree at most 1. This might be black. This might be a black edge. I don't know if this is in the complement, but I know that, oh, that's not good. I know that these 3 edges must be black. Okay, now what am I looking for in the complement? What am I looking for in the complement? How big a cycle? 3. So let's label all the vertices. A, B, C, I guess D and E. So what if CD is black?
Done.
Y'all are colorblind, so you can see that these are black edges and this is red edge. Okay, what if CD is black? I would have a K3. Is that clear? And if DE is black? And if CE is black? But all the edges have to be either in the graph or in the complement. So this is not black, and this is not black, and this is not black, so they all must be red. But what? You can say it, but then this is a P3. Okay, so one more time, the graph in this case, for every graph on 5 vertices, either it contains a P3 or its complement contains a K3. Okay, and this concept of looking at a graph and its complement, I mean, we've got several weeks or maybe months before we get to it, is an important concept in graph theory. What's the relationship between what's subgraphs that are in the graph versus subgraphs that must be in the complement? So there's a relationship. Now, several people asked me about P4. Several people tried to prove this, where I'm going to put quotes around P3. P3 is this. P3 is that. Okay, I claim then if you tried to prove that P3 was that, then it's not true. Okay, and here's my proof. Okay, that's the graph G. Now, what are we looking for in the complement? by the way, one more time, there's no P3 as you've mistakenly defined it over here. No P3. This is the graph. What does the complement look like? Sorry, one more edge. One more edge. I gotta have that edge. Sorry. Okay, so one more time. This is the graph G. What does the complement look like?
A double.
Okay, there's 2 vertices that are independent here, and 3 vertices that are independent up here, and all of these are adjacent in G, and all of these are adjacent in G. So where are all the edges in G complement? Okay. So is there a C3? Someone say there's no C3.
No.
There's a C4. By the way, there's no C5. There is a C4, but there's no C3. And although they call it C3, really C3 is a K3. Okay. Now, this idea of, again, a graph and a complement, I'm going to give you another problem I want to actually go through. I want you to take a few minutes and show that for any graph on 6 vertices. Oh, by the way, did I show you that, in fact, if you went down to 4 vertices, you thought it was true for 4 vertices. It's not. Okay? So you might want to think about how we can show that that's not the case. For any graph on 6 vertices, any graph G on 6 vertices, either G contains a K3, or G complement contains. Okay, take a minute and see if you can prove that.
For any graph G.
On 6 vertices,
Okay.
either G contains a K3 or G complement contains a K3.
Oh, you put any, okay, no, so, because I'm saying then you're- gotcha. So, right here. So.
Oh yeah, this is the party problem.
Yeah. Have you seen it before?
Yeah.
So,
This is the end result.
yeah.
Which do you? Okay, so.
Who'd you see it?
Let's see. I'm taking topics.
Oh,
And so, literally like 2 weeks ago.
cool. I had an algorithms test in the computer science department, and she had a question on there like this.
Pretty quiet.
It was like
You can talk to your neighbors.
17 people and a K4.
Gotcha. There was one where it was, oh yeah, the Ramsey numbers. is what they
Exactly,
call it. So
yeah.
you need 18.
Oh,
And then
18.
you can guarantee that there's a K4
Yeah.
in one.
That was an odd.
No, sorry, no, not a K4, a C4
Right.
is what you're looking for
Okay.
with the Ramsey. Maybe we're talking about 2 different things, but
No.
If we're talking about the
This was the
Ramsey,
problem.
yeah.
Basically, he no, there's at least
Yep.
9, and
Yep.
then,
And part of that one, you have to show that within the 9, you have either a square in the graph or a triangle in the, so a C4 in G or a C3 in G complement.
was
For the, for the
But-
K4, I feel like would be, you would need more than 18. Because with, so yeah, so the way it goes is we got 18, you have 1, 17 others, so that's gonna have at least 8 things.
Mhm.
Okay, so here we have 9. So we want either, wait, so you say, okay, so, okay, so there's 8 here, so you say, 3 have gotta be one color.
Well, so you would have 9 coming out of this vertex, right? Because there's,
K3 in this graph.
the maximum degree would be 17.
So if you don't have K3 in this
Well,
graph,
I think you need
But-
18
first we
vertices to
set
guarantee,
the path.
Oh, you mean like in this
Contains
neighborhood?
3 point in this graph.
well,
Or
18 total
we can
to
Right.
find the
guarantee
path
there
contains
exists a
the 2
monochromatic square.
So there would be, the neighborhood
vertices
of
in
each
this
would be
graph,
like
and
17, and then
Mhm.
one of them has at
Obviously,
least
number
9.
of paths contains the,
Yeah,
Because
so
the
so
more
so
than
there's
three
so
vertices
yeah,
are
so there's
that's the first.
So there should be
17
one
vertices.
more.
The another is in the number of paths
Okay, but-
contains
but-
less than 3 vertices in this graph.
so then of
which
that,
means,
at least
it's
9 are one
true,
color. I see.
Or it's all these.
Right.
Okay, so then you say
So for this
you've got some
situation,
cases.
we can always find.
Either these 3 are one
Yeah.
color.
So if the number
Well,
of
and the
paths,
reason 9
we
is
can always
significant
find
here is
3
because
vertices
the split is
that
5
are
and 4.
connected with each other.
Mhm. And if you split 5 and 4, then that graph can't
So, yeah, we
exist.
can find 2 here.
Or no, hold on. Gosh, I just wrote all this out.
They are disconnected with each other. This means the counterpart of the
Well, the neighborhood of one of these,
reversible.
Okay, not that I want to remind you of bad things, but
Which is
how many of you took Math 3000? Funny how that is, everybody, right? I claim that this is just a pigeonhole principle. Okay, so what the pigeonhole principle, you gotta remind me, you can even tell me what it is with pigeons.
So if you have 5 holes and 6 pigeons, there has to be, there has to be at least 2 more.
Okay, so one more time, if there's 5 holes with 6 pigeons, there has to be at least 1 hole with 2 pigeons. And in general, if you have n pigeons flying into k holes, and I'm saying this now because the pigeonhole principle comes up a lot in this class. If I have n pigeons flying into k holes, hopefully k is less than n, then there's some hole that has more than 1 pigeon. Okay? What does this have to do with graphs? Okay, so I'm going to choose any vertex. In the complete graph, there's an edge from that vertex x, from x to these 5 vertices. And the 2 holes my pigeons are flying into is that x is adjacent to a point, or x is not adjacent to a point. So my pigeons, I have 5 pigeons, so it's either adjacent to it or not adjacent to it. So I have 5 pigeons flying into 2 holes. So what can you tell me? What?
2 to the 5th.
There's 2 to the 5th, that's much too many. I mean, apply the pigeonhole principle. 5 pigeons in 2 holes. Either the edge is there, the edge x to this vertex is there, or the edge x to this vertex is not there. So one more time, there's 2 holes. 2 holes, imagine 2 holes. Edge, non-edge. What can you tell me? Okay, so again, my pigeon, this pair, this pair, this pair, this pair, and this pair. 5 pigeons, 2 holes. You told me what the pigeonhole principle was. Didn't you?
So 1 hole has more than one.
Oh, no, you can do better than that. One hole has
More than 3.
more, 3 or more, right? One hole, either edge or non-edge, has at least 3 pigeons in it. Let's look at the edge hole. Let's assume that X is adjacent. That's not, okay. Red is now adjacent. Let's assume that red is adjacent to 3 vertices. Well, what can you tell me about, let's label these, 1, 2, 3. What if 1, 2 is red? If 1, 2 is a red edge, then I have a red K3. If 2, 3 is a red edge, and if 1, 3 is a red edge. So if any one of these edges is red, we would have a red K3. Well, if they're not red, what are they? Oh, so if they're all black, then what do I have?
Another
I
K3.
have a black K3. So for any graph G, now turn this into, the red edge means the edge is there, and the black edge means that the edge is not there. So either there is a red K3, there's a three vertices that form a K3, or there's 3 vertices that form a K3 in the complement. So the black edges would correspond to the complement. Okay, is that clear? This is a fundamental theorem in graph theory, and we'll talk about him much more. Okay, this is part of Ramsey's theorem. Okay, and he was in the late 20s. He was one of the fundamental developers of graph theory. Okay, now the question is 6 the smallest? So let me change this. For any graph G on 5 vertices, either G contains a K3 or G complement contains a K3. So now it's a question. Is it true for any graph G on 5 vertices, either G contains a K3 or G complement contains a K3? That's a question. Think about it. Is that true? Think it's true? So you can go through the same proof?
I think so.
Okay, so let's see what happens. So I have 5 vertices. I'm going to choose some vertex X. And now I have how many more vertices?
4.
4. X can't be black to 3 of them. One more time, if X is black to 3 of them or red to 3 of them, then I would have a K3. So if X can't be black to 3 of them, and there's only 4 vertices, then it must be black to 2, and my 2 colors are black and red to 2. Can you see those colors? I can't. Let's label the vertices. 1, 2, X1, X2, X3, X4, X5. And can you see which ones are black? I can't. These are black. No, these are black. And these are red. So let me just, the easy question, if I'm trying to avoid black K3, what can you tell me about the edge X1, X2? Must be what? Red. Okay. X1, X2 better be red. And what about X3, X4? Black. Rather than draw it like this, I'm going to draw it like this. Okay, suppose that's the black graph. Is there a black K3? What's the red graph look like? It looks different, but what is the red graph? What?
C5.
C5. Okay, so we have a red C5, and I have a black C5, and that's all the edges, all the possible edges on 5 vertices. Does red C5 contain a red triangle? Does black C5 contain a black triangle? So 5 is not enough. So 6 is the smallest such number of vertices so that this is true. So now let's go back, finally let's go back to the problem you had, because several people wanted to prove something much more general. So I want to find either the graph contains, either the graph contains a P3 or a C4, a P3 or a C3. Every graph on 3 vertices either contains a P3, every graph on, how many vertices? 5? Every graph on 5 vertices either contains a P3 or the complement contains a C3. And we proved that. So the question is, what about 4 vertices? One more time. We showed that if you take any graph on 5 vertices, then it either contains a P3 or the complement contains a C3. So now it's a matter of finding, can you find a graph on 4 vertices that doesn't contain a P3 and the complement doesn't contain a C3? I'm seeing some head shaking. It's not hard. 4 vertices. Okay. That graph contains, does that graph contain a black P3? What does the complement look like? I'm going to draw it in, and then I'll draw it that's what the red graph looks like. So just so that you can see what it is. Does that graph contain a C3? No. Okay. So in fact, 5 was right. The problem as it's written is right, and it's the best you could possibly do. Okay. Questions about that? Okay. So I'm going to give you a problem now. I want you to think about it for Thursday, and then we'll start with, we'll come back and go through trees again starting Thursday. What about, so I'm going to ask, what's the smallest end so that any graph of order n, I'm going to erase part of this, any graph of order n contains a P4 or the complement contains a P4. P4. Okay? So we did P3, C3. We did K3, K3. Now I'm asking for P4, P4. And then what I want you to, I want you all to become research graph theorists. MN. So how large a graph do you need so that either the graph contains a red PM or the complement contains a black PM? So again, I'm talking about the graph is red and the complement is black. Okay, so starting with we know some small values, 2s and 3s and 4s maybe. No, I don't know any 4s. Maybe the place to start is 4 and 4. Or maybe the place to start is even 4 and 3. So what is the smallest n so that any graph of order n contains a P4 or the complement contains maybe a P3 would be a better place to start, or P4 and P4. But see if you can come up with a general formula for PM and Pn. So any graph of course, sorry, let's see. I don't want you to be confused. This n is different than this n. So let's see. So contains a, let's say, P M and a P J. So either the graph contains a P, what did I say, PM, or the complement contains a PJ. Okay? And I want you to be thinking about how you might attack this problem. Okay? Questions about that? Okay, I'm gonna end class there. Unless you have questions, and we'll pick this up, and we'll get back to trees on Thursday.
We have the study materials that we're gonna work on with Stetson, so we can have them over the weekend?
No, that would mean I'd have to make them up. Yes, as soon as I make them up, I'll put them on camera.
What was the question?
Okay, so there's a test. When's the test? Next Tuesday, week from today. Oh, it's hard. I would imagine you could probably all. There's going to be some definitions, and I'll go through a little bit about what I'm expecting you to know on the test. By the way, there will be at least one proof on the test. Okay? Questions? See you Thursday.
I think it has to do with you have a neighborhood of 6, so there's a triangle here.
Yeah.
And then the next neighborhood also has a neighborhood of 6, which is not intersecting this at all.
Okay, so here, I got this.
Oh yeah, hold on.
Yeah.
You haven't turned it in. Put it up on the.
Okay, so the question is, just to make sure we're on the same page, the question is, we want to show that with 18 vertices, there exists a monochrome
No.
square.
Sorry, the test is
Is that what we're
Thursday.
asking? Or are we-
Stetson
I'm not
will
sure
do a
which
review
direction.
on
I don't know if it's
Tuesday.
a square or a K4. I think it's.
I'm sorry.
I feel like it's a K4, but I don't know.
So,
When we're talking like this,
oh, okay,
if
and
it's a 4, then I think that applies.
so the one I did was for a square.
Okay.
And that's
Oh
where
my
I'm
God.
confident on the number 8.
Okay.
If we do a different problem, then obviously.
I saw you
But,
doing it during
okay,
class.
so you get 1 and then 17 vertices all around. So you're gonna get at least 9 of those 17 vertices have the same color. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay.
今天要出去，今天要出去，后天我要去帮你们。
Okay, so then it was we've got 3 cases. One case is that you have. Okay, let's say all these are reds. One case is that you have at least 6 blues. 4, 5, 6. And then if you have 6 blues, then you've got